right, hello. Just thought I'd go ahead and finish up our notes right now, so I can post these tonight, and you can do them at your leisure anytime between now and next class. So we're going to be finishing up talking about buffering capacity, and basically what that means is what range of pH will a buffer system work. Like I said, buffers will resist changes in pH when we add a strong acid or strong base to them, but there is a limit. So they will only, be fairly consistent in their maintaining a fairly constant pH up to a point. So that's what we mean by buffering capacity, or the pH range of what range will that buffer work within before it won't work anymore. So the amount of acid or base that the buffer can neutralize, like I was showing you earlier in your notes, if we add a strong acid to the buffer, it will react to an acidic buffer. It will react with the conjugate base to form more weak acid. Or if we add base to it, the base will react with the hydrogen ion in the acid to form more conjugate base. So how much of that strong acid or base can we add, and the buffer will still neutralize that and keep the pH fairly constant. So that's what we're going to look at here. And then the pH range just shows the distance in pH of the smallest to largest pH, that it will still be an effective buffer. So typically the way we can calculate the pH range of the buffer is it will work within plus or minus 1 pH value of its pKa. So like for acetic acid, again, acetic acids, Ka is 1.8 times 10 to the negative fifth. So if we convert that to pKa, I'll do it right this time, by taking the log of 1.8 times 10 to the negative fifth, that gives us, that equals 4.74. So that's the pKa for acetic acid. So that means a buffer that contains acetic acid and its conjugate base, acetate, sodium acetate or whatever, the acetate ion, it will work within a range of pH from 3.74 all the way up to 5.74. So that's an effective range. So that's also another common AP question, a multiple choice question. It could give you a list of Kas or even pKas and ask you, which one would be an effective buffer in this particular pH range. So it's plus or minus 1 of whatever that pKa is. And so, if we were matching up, if we knew what pH range we wanted, we would just find a weak acid with its salt that would have a pKa close to that desired pH. So again, as we talked about before, this little diagram shows how buffers are able to resist drastic changes in pH even when we add a strong acid or strong base to it. So the strong acid or strong base gets completely used up. So if we add a strong acid, the extra H plus, so like here, this part of the diagram showing we're adding a strong acid to the buffer solution. So the extra hydrogen ion, because this again completely dissociates since it's strong, the extra hydrogen ion reacts with reacts with the conjugate base to just form more of the weak acid. So again, it's not going to change its pH. Oops, I think I blocked out my picture. Sorry about that. So same thing when we add a strong base. And that's what this is showing down here. We're adding a strong base. Again, the cation stays dissociated. It's a spectator ion, but the hydroxide ion reacts with the hydrogen ion of the weak acid to form just more of a conjugate base of that weak acid and water. So again, we're not changing the pH much at all. It does tweak it a little bit with both of these cases, but it's really not going to change much at all. Oops, okay. Let me make sure. I didn't want to add anything else before we go on. No, I think that's everything. Okay, and then again, we calculate pH or POH, but again, even if we're dealing with a basic buffer, everything's the same, just in reverse. And then obviously we'd be solving for hydroxide ion and POH, and then have to convert it to pH. But usually we talk in terms of acids and pH. But we could do this with basic buffers as well. Okay, then our final slide here shows how we can do a calculation. Again, acetic acid, that's probably our most common weak acid that you'll see a lot of. So we have 3 moles of that, as well as 3 moles of the salt of that weak acid, so sodium acetate, which again, the sodium is a spectator ion because it's the cation of a strong acid, so it's not going to do anything. It's going to stay dissociated. And so it's in a 1 liter solution. So even though this is given in moles, because it's a 1 liter solution, the moles and molarity concentration are the same. So we can call that 0.3 molar, or just use it as 0.3 moles. And then the pH of the buffer is 4.74. So we want to figure out what the pH would be after we add 5 milliliters of 4 molar sodium hydroxide. So we're adding a little bit of strong base. So we want to see how will that affect the overall pH. It's going to change a little bit, but not a lot, considering that we're adding a really strong base to a fairly weak acid. So again, if we set up our reaction, and again, it doesn't matter if we use the actual formulas or not. So we have our weak acid and its conjugate base. Okay, so we have, and in this case, and we'll talk more about this next week when we do titrations. We'll have to do stuff very similar to this when we're talking about titrations. We do have to take into account that we're adding 5 milliliters to our total volume. So you'll see as we go in here, and that's why that's given in moles, just so we don't have to convert back and forth. So when we're adding and subtracting amounts of stuff being added, it's best to do it in moles, and then when we're ready to do the calculations, then we can convert it back to molarity using our overall total concentration. So you'll see that here as we go. So first, let's look at our initial, set up our ice table. Okay, so our initial concentrations are for our acetic acid. Oops, I always do this too close. Let me scoot this out a little bit farther, because ultimately we're going to add in hydroxide ion. So from our sodium hydroxide. Okay, now let's set up our ice table. You can still see that. Yes, you can see that. Okay, so initially we have, again, do it in moles first. here's our buffer of 0.3 moles of our weak acid. We also have our common ion, 0.3 moles of our acetate ion, and we have 0, 0. Okay, so then we're going to add in. Where do I want to do this? Where can you see it best? I'll do it down here. We're going to add in 4 molar, which moles over liters, and we're doing 5 milliliters, 0.0050 liters of NaOH. So that is equal to, what is that equal to? 0.02 moles of hydroxide ion. So that is our change. We are adding 0.02 moles of hydroxide ion. But as that diagram on the previous page shows, the hydroxide ion is going to react with the hydrogen ion. So this is going to go down. The amount of weak acid is going to go down by 0.02 moles. And as it reacts with the hydrogen ion, it's going to cause the anion, the conjugate base, to increase by 0.020 moles. So then, well, and I wrote this as, let's just, let me fill this in as water. We don't need to, there we go. Okay, so then at equilibrium, now all of this, all the way up to, we can add all the way up to 0.3 moles of base before the buffer won't work anymore. So as long as we still have some acid left over, the buffer will still work. But all of this base is gone. It gets all used up, reacting with the H to form the conjugate base, and that leaves us with 0.0280 moles of acid. And again, we reacted the hydroxide ion to make this conjugate base, so that goes up to 0.320 moles of our conjugate base. So then we can plug in our we can either do this at we can do this with the Henderson-Hasselbalch equation, or we can do this with the Henderson-Hasselbalch, or we can do it the old-fashioned way with the equilibrium thing. But before we plug in any of these numbers, remember these were in moles. That's what we have to use when we're adding volumes together. So before we plug these values in, we have to convert these back to molarity by dividing them by our total concentration, which now our total concentration, we had 1 liter to begin with, and now we have 1.05 liters. So this is, where is this? So we're going to divide this by 1.05 liters to get our actual concentrations, which I thought I had that, but I didn't. Okay, so 0.028. So that gives us 0.027. So that equals 0.0277. We'll keep 3 sig figs. That's our concentration of our acid. And then same thing, so 0.32 divided by 1.05. That gives us 0.304. So that equals 0.305 molar for our for our conjugate base here, the acetate ion. So I'm going to go ahead and use the Henderson-Hasselbalch equation because it gives us the pH. Otherwise, we could convert that to hydrogen ion concentration, but it's just easier this way. So again, the Henderson-Hasselbalch equation, let me erase this, is pH equal to pKa plus the log of the acetate ion over the concentration of the acid. Okay, so it gives us the 4.7, where am I? So we have 4.74, that's actually our pKa that we calculated on the previous page. And then we plug in, our log of 0.305 over 0.0277. So let's see what that is. 0.305. Okay, I need Sarah here to show. I had an extra 0 in here, 0.2. I was going to say that didn't seem right. Okay, let's try that again. So it should be 0.30 minus 0.02 is 0.280. So let's try that again. So 0.28. So that's 0.2. 267. There we go. I was going to say that's way too small. Okay. Here we go. Okay, let's try that again. So 0.305 divided by 0.267, and then we take the log of that. So that is equal to 0.056, and then we add that to, which really 0.057 actually, if I round that up, 0.057, and then we add that to 4.74. So you can see, even though we added 5 milliliters of a strong base to this weak acid, that's only going to cause the pH to go up to, so our new pH, when we add these two values together, becomes 4.80. So it only went up by 0.06 because, again, this hydroxide ion was completely consumed by the weak acid, and we just increased the conjugate base a little bit. So that's why it did become slightly more basic, but not as much as you would think from adding a strong base. Oops. Can you see that down there? There we go. Okay, so again, just sometime before next class, try and do the homework, and obviously we'll go over questions that you'll probably have some questions on that. Before you turn it in, you can always shoot me an email as well. So have a good weekend, and I'll see you Monday morning for office hours for the Part 2 mock exam. Bye.